Hello. Hello and welcome to this video. In this video, we will go through the composite types of PostgreSQL. We have covered still arrays, and then we have range types, domain types, object identifier type, and PDA type, followed by CV types. So not much remains in this chapter. We will try to cover as much as possible. So let's start the read through. A composite type represents the structure of a row or record. It is essentially just a list of field names and their data types. PostgreSQL allows composite types to be used in many of the same ways that simple types can be used. For example, a column of table can be declared to be of a composite type. So here are two examples. One is the complex, where the real part and imaginary parts are described as double. So complex will represent a complex number having two parts. Then we have inventory item part where name, supplier ID, and price are there of type text, integer, and numeric respectively. Note the declaration syntax. We have create type, then type name, as, and then the fields. The syntax is comparable to create table except that only field names and types can be specified, not constraints can presently be included. Note that the as keyword is essential. Without it, the system will think a different kind of create type command is meant and you will get odd syntax errors. Having defined the types, we can use them to create tables. So we have a table on hand in which item inventory item is there and count is also there. So how do you insert it? So for the value inventory item, you have to cast it to a row and then give the elements. For example, for the item, the supplier ID and price. Or we can create functions of this. Create function price extension. It takes inventory item and integer and returns numeric. And select $1.price. So price of inventory item and multiplies it by 2 and it returns that. So select price item, comma 10 from my hand. Whenever you create a table, a composite type is also automatically created with the same name as the table to represent the table's row type. For example, had we said create table inventory item, name, text, supplier ID, integer, references, suppliers, price, numeric check, price greater than 0, then the same inventory item composite type shown above would come into being as a byproduct and could be used just as above. Note, however, an important restriction of the current implementation, since no constraints are associated with the composite type. The constraints shown in the table definition do not apply to the values of composite type outside table. To work around this, create a domain over the composite type and apply the desired constraints or check constraints of the domain. Now we'll see how we can construct composite types. To write a composite value as a literal constant, enclose the field value within parentheses and separate them by commas. We can put double quotes around any field value and must do so if it contains commas or parentheses. Thus, the general format of a composite constraint is the following. Within single quotes and within parentheses, you give val1, val2, and so on. So, for example, this fuzzy dice one is given, which would be a valid value of inventory item type defined above. To make a field be null, write no characters at all in its position in the list. For example, the constant specifies a null search field like this. So in this case, price will be null. If you want an empty string rather than null, write double quotes like this. Here the first field is non-null empty string, third is null. These constants are actually only a special case of the generic type constant discussed in section 4.1.2.7. The constant is initially treated as a string and passed to the composite type input conversion routine. An explicit type conversion might be necessary to tell which type to convert the constant to. The row expression syntax can also be used to construct composite values. In most cases, this is considerably simpler to use than the string literal syntax since you don't have to worry about multiple layers of quoting. We already used this method before. So these are the ways using row keyword. The row keyword is actually optional as long as you have more than one field in the expression. So these can be simplified to like this. The row expression syntax is discussed in more detail in section 4.2.1.2.13. Now, how do we access composite types? To access a field of a composite column, one writes a dot and the field name, much like selecting a field from a table name. In fact, it is so much like selecting from a table name that you often have to use parentheses to keep from confusing the parser. For example, you might try to select some subfields from our on-hand example table with like this. Select item.name from on-hand where item.price greater than 9.9. This will not work since the item is taken to be a table name, not a column name of on-hand. For SQL syntax rules, we must write it like this. Select within parentheses item.name from on-hand where item.price greater than 9.99. Or if you need to use table names as well, like this, select on-hand.item from .name from on-hand where on-hand.item the price greater than 9.99. So see how parentheses are used to surround the composite type. Now the parenthesized object is correctly interpreted as a reference to the item column and then the subfield can be selected from it. Similar syntactic issues apply when you select a field from a composite value. For instance, to select just one field from the result of a function that returns a composite value, you need to write something like this. Select within parentheses myFont field dot field from. Without the extra parentheses, this will generate a syntax error. The special field name star means all fields as per the explained in section 8.16.5. Now, how do we modify the composite types? So we have some examples. Insert into my tab complex call values 1.1 2.2 and update my tab set complex call is equal to row 1.1 2.2 where the first example omits row, the second uses it, we could have done it either way. We can update the individual subfield of a composite column. Update my tab set complex call dot r is equal to complex call dot r plus 1 where notice that we don't need to put parentheses around the column name appearing just after set. We do need parentheses when referencing the same column in the expression to the right of the equal sign. And we can specify the fields as targets for inserts too. Insert into my tab complex call.r complex call.i values 1.1 2.2. Had we not supplied values for all the subfields of the column, the remaining subfields would have been filled with null values. Using composite types in queries. There are various special syntax rules and behavior associated with composite types in queries. These rules provide useful shortcuts, but can be confusing if you don't know the logic behind them. In PostgreSQL, a reference to a table name or alias in a query is effectively a reference to the composite value of the table's current row. For example, if we had a table inventory item as shown above, we could write select C from inventory item C. This query produces a single composite value column, so we might get output like this. We have this output row C. Note, however, that simple names are matched to column names before table names, so this example works only because there is no column name C in the query tables. The ordinary qualified column name syntax table name dot column name can be understood as applying field selection to the composite value of the table's current row. For efficiency reasons, it is not actually implemented that way. When we write select C dot star from inventory item C, then according to SQL standard, we should get the contents of the table expanded into separate columns. And if the query where C.name, C.supplier, C.price from inventory item C, PostgreSQL will apply this expansion behavior to any composite value expression, though as shown above. Although as shown above, you need to write parentheses around the values that dot star is applied to whenever it is not a simple table name. For example, if my func is a function returning a composite type with columns A, B, C, then these two queries have the same result. Select myfunc x dot star from some table and select myfunc x dot a, myfunc x dot b, myfunc x dot c from some table. PostgreSQL handles column expansion by actually transforming the first form into second. So in this example, myfunc would get invoked 3 times per row with the other syntax. If it is an expensive function, you may wish to avoid that, which you can do with the query like select m dot star from some table lateral myfunc x as m. Placing the function in a lateral form keeps it from being invoked more than once per row. M dot star is still expanded to M dot A, M dot B, M dot C, but now these variables are just references to the output of the from item. The lateral keyword is optional here, but we show it to clarify that the function is getting X from some table. The composite value dot star syntax results in column expansion of this kind when it appears at the top level of select output list. A returning list in insert, update, delete, merge, a value clause, or a row constructor. In all other contexts, including when nested inside one of these constructs, attaching dot star to a composite value does not change the value, since it means all columns, and so the same composite value is produced again. For example, if some func accepts a composite valued argument, these queries are the same. Some func C dot star from inventory item C, select some func C from inventory item C. In both cases, the current row of inventory item is passed to the function as a single composite valued argument. Even though dot star does nothing in such cases, using it is good style since it makes clear that a composite value is intended. In particular, the parser will consider C in C dot star to refer to a table name or alias, not to a column name, so that there is no ambiguity. Whereas without dot star, it is not clear whether C means a table name or a column name. And in fact, the column name interpretation will be preferred if there is a column name C. Another example demonstrating these concepts is that all queries mean the same thing. Select star from inventory item C, order by C. Select star from inventory item C, order by C dot star. Select star from inventory item C, order by row C dot star. All these order by clauses specify the row's composite value, resulting in sorting the rows according to the rules described in section 9.25.6. However, if inventory item contained a column named C, the first case would be different from the others, as it would mean to sort by that column only. Given the column names previously shown, these queries are also equivalent to those above. Select star from inventory item C, order by row C dot name, C dot supply ID, C dot price. Select star from inventory item C, order by C dot name, C dot supply ID, C dot price. The last case uses a row constructor with the keyword row omitted. Another special syntactical behavior associated with composite values is that we can use functional notation for extracting a field to a composite value. The simple way to explain this is that the notations field table and table.field are interchangeable. For example, these queries are equivalent. Select C.name from inventory item C where C.price greater than 1000, or select name C from inventory item C where price C greater than 1000. Moreover, if we have a function that accepts a single argument of a composite type, we can call it with either notation. These queries are all equivalent. Select some function C from inventory item C. Select some func C dot star from inventory item C. Select C dot some func from inventory item C. This equivalence between functional notation and field notation makes it possible to use functions on composite types to implement computed fields. An application using the last query above wouldn't need to be directly aware that some func isn't real column of the table. Because of this behavior, it is unwise to give a function that takes a single composite type argument the same name as any of the fields of the composite type. If there is ambiguity, the fixed name interpretation will be chosen if field name syntax is used, while the function will be chosen if function call syntax is used. However, PostgreSQL versions 4.11 always chose the field name interpretation, unless the syntax of the call required it to be a function call. One way to force the function interpretation in older version is to schema qualify the function name, that is right, schema.func composite value. Now we will look at composite value input and output syntax. The external text representation of a composite value consists of items that are interpreted according to the IO conversion rules for the individual field types, plus decoration that indicates the composite structure. The decoration consists of parentheses around the whole value plus comma between adjacent items. White space outside the parentheses is ignored, but within the parentheses it is considered part of the field value and might or might not be significant depending on the input conversion rule for the field data type. For example, in this example, that is, we have space before 42, the white space will be ignored if the field type is integer, but not if it is text. As shown previously, when writing a composite value, you can write double quotes around any individual field value. You must do so if the field value would otherwise confuse the composite value parser. In particular, field containing parentheses, commas, double quotes, or backslashes must be double quoted. To put a double quote or backslash in a quoted composite field value, precede it with a backslash. Also, a pair of double quotes within a double quoted value is taken to represent a double quote character, analogously to the rules of single quotes in SQL literal strings. Alternatively, you can avoid quoting the use backslash escaping to protect all data characters that would otherwise be taken as composite syntax. A completely empty field value, no characters at all between the commas or parentheses, represents a null. To write a value that is empty string rather than null, write double quotes without space. The composite output routine will put double quotes around field values if they are empty strings or contain parentheses, comma, double quotes, backslashes, or white space. Doing so for white space is not essential but aids legibility. Double quotes and backslashes embedded in field values will be double. Remember that when you write in an SQL command will first be interpreted as a string literal and then as a composite. This doubles the number of backslashes you need assuming escape string syntax is used. For example, to insert a text field containing a double quote and a backslash in a composite value, you need to write backslash before double quote and two backslashes for a single backslash. And then we have double quotes for the entire string. The string literal processor removes one level of backslashes so that what arrives at the composite value parser looks like this. In turn, the string fed to the text data types input routine becomes double quote backslash. If we were working with a data type whose input routine also treated backslash, especially by key, for example, we might need as many as 8 backslashes in the command to get one backslash into the stored composite field. Dollar quoting can be used to avoid the need to double backslash. The row constructor syntax is usually easier to work with than the composite literal syntax when writing composite values in SQL commands. In row, individual field values are written the same way they would be written when not members of a composite. So now we come to the usefulness of composite type. They are quite useful when you have to store data which are related. For example, if we have a field or other fields from, say, a government issued ID. For example, a driving license could have name, date of birth, blood group, date of issue, and date of expiry, date of birth. Then it makes sense to combine them as composite type. So you should be generous when using composite types. It is not a complicated thing to do. It just needs a bit of practice to insert and takes a bit of discipline. It might be confusing because it is not used as much as it should be. Okay, so practice the syntax and then composite types will be basically as simple as normal fields. So with this, I will end this video and I hope that you are enjoying this read through and finding it useful. So I'll see you in the next video and we will study range types in the next video. So thank you for watching the video. I'll see you in the next one. Till then, enjoy.